in the last class, we solved till question number 11, correct? So we proved that a function is continuous on R if and only if we have an open set in the codomain set, the pre-image of that open set is also open in R. Okay. So let's start solving from question number 12. What is going on? Okay, it's not working fully. Okay, then. Yeah, that's leave it. Okay, let it be there. Okay, look at the question number 12. Okay, so all of you have this tutorial sheet, but I have modified a little bit because I have included a few extra problems. So anyway, the functions, we have two functions, f and g, both are continuous on R. Then we have to show that the set of all real number where fx not equals to gx is open in R. Okay. So try to solve it. So then I will see. Okay. You can solve this question directly to prove that this set is an open set, or you can use the sequential criteria to show that the complement of this set is a closed set. Okay, both are fine. If any online participant want to answer, he or she can answer. Please raise your hand if you want to answer. Okay. Okay, any guess? How shall we approach? We can. Okay, yeah, that can also be used. Okay, so there are different ways you can solve this problem. What's the set? So form a new function fx hx, which is fx minus gx. So then you have a continuous function. So then it will map, not map. Then pre-image of a closed set will be closed. So take singleton 0. The pre-image of that singleton 0 will be closed set. So therefore, it will be its complement set will be a closed set. Okay. Or okay, let's see. So what's the set? So question number 12. So define a new function h of x is fx minus gx. Then this set all x belongs to R such that fx equals to gx is same as the set x belongs to R such that Hx equals to 0, and which is nothing but the inverse image of this singleton set 0. Now singleton 0 is a closed set. So pre-image, because H is a continuous function, pre-image of the closed set is closed. So therefore this set is a closed set and we are done. Okay. So there are different ways you can approach if you are not compatible with this idea. So what you can try to show that. So let's say this set is A, which is all x belongs to R such that fx equals to gx. Okay. So let T be a limit point of A. Okay. So what we'll do, then we have a sequence from elements of A which will converge to the point C. Okay. So then there exists a sequence Cn of elements of A converges to C. Okay. So now what will happen? If we can show that C is in A, then A contain all its limit points, therefore it's a closed set. Okay. Now Cn converges to C, it means, now see that because Cn okay, just yeah, because f is continuous in whole of R, so what you have, f of xn converges to f of c and g of xn converges to g of c, since both f and g are continuous at c, correct? Now because, sorry, not xn, this is cn. Okay, okay, let me erase this. So f of cn converges to and g of cn converges to g of c. Now both, because cn are elements of A, so f of cn equals to g of cn. Okay, since cn belongs to A, f of cn is equals to g of cn for all n belongs to n. So now this only possibility is that f of c equals to g of c, because both cn and gn are same sequence, both are, so f of cn converges to f of c and gn is g of cn converges to g of c. So only answer we have f of c equals to g of c. Now f of c equals to g of c means c is an element of A. Okay. So consequently c is an element of A and hence C contains its limit point. So therefore A is a closed set. Okay. So this is another way you can solve it. Or you can directly prove that A is an open set. Not A, that what if the whatever the set you are setting, that all x where fx not equals to gx is an open set. Okay. Is it clear? Both way you can solve it, this way or that. Or there are many different way you can solve the question. Okay. Question number 13. If f and g are continuous on R and fx equals to gx at all rational points, then fx equals to gx for all x belongs to R. So how to solve it? Obviously sequential criteria, but I will recommend you to solve this question using question number 12. How to use question number 12 to solve this problem? No, we just use the fact the fx not equals to gx. Now fx equals to gx means we already learned that set is a closed set. Okay. So what will happen? Question number 13. Let A is the set where x belongs to R such that fx equals to gx. Correct. And we observed that A is a closed set in R. Now, what is given? What is given in the question? Look at the question again. F of x equals to g of x at all rational points. That means the set of all rational number is contained inside the set A. Okay. Sorry. So, given that Q is a subset of A. Set of all rational subset of A. So then what? What we can do after this? We have to show that this set A is whole of R. How to show it? Q is a subset of R. Then what we can do? Yeah, closure, not dense. Yeah, I mean ultimately then closure of A is a subset of closure of A. But closure of Q is whole of R and closure of A is equals to what? What is the closure of A? A itself. So thus R is a subset of A. Hence A equals to R. So this proves that fx equals to gx for all real numbers. Okay. It is actually the whole thing. If you look at the proof, as he said, if you consider instead of rational number, if we have a set of all irrational number, still this statement will be true. Or if we have any dense set, then still the statement will be true. Dense in the sense that if the closure of the set is equals to whole of R. Okay. So then the statement will be true here as well. Okay. So only this is the fact we used in this proof basically. And A is closed, whatever it is, whether it fx and gx are equal in a, for all rational points or not does not matter. Okay. Okay. Question number 14 is very easy, but try to solve it. Let f from R to R be continuous on R and let C belongs to R such that f of C is greater than 1. Okay. 1 is not a partial number, just if we have any number at which f of C greater than 1. Prove that there exists a neighborhood U of C such that f of x greater than 1 for all x belongs to U. So how to prove? Actually, I should mention that you don't need the function f to be continuous on all of R. You just need that function is continuous at the point C. That's enough. Okay. So let's say you have a function f which is continuous. Okay, so I am giving you the what is given to us. Question number 14. Given that 1 f is continuous at C, second f of C greater than 1, what you have to show? To show there exists a neighborhood U of C such that f of x greater than 1 for all x belongs to U. Okay. Any idea how to approach? Use the epsilon delta definition. Epsilon equals to correct. Then correct. Anyone else? Okay. But what is that neighborhood for which f of x will be greater than 1? Okay, okay, I got it. What you were saying. Okay, that's also a good approach. Okay, so we got two different approaches to solve this problem. One is that, as he said, so first approach or second approach, better, whatever. So he's saying if you consider V as 1 comma infinity, so this is open in R. Okay, is open in R. Okay. So then F inverse V. So in that case, you have to use the fact that F is continuous in whole real line. Okay. But suppose we only have, okay, so let's say function is continuous in whole real line. Let's see what is going on. F inverse V is open in R. So obviously V contain f of c because f of c is greater than 1. So V will be, so clearly f inverse V is the neighborhood of C for which the statement is true. Okay. This is a good approach if we consider that f is continuous in whole real line. But now we only have that f is continuous at the point C. Then what we can do, as she said, let epsilon equals to f of c minus 1. Why it is possible? Okay. Then f of c is greater than 1. Why it is possible? Because f of c is greater than 1. Okay. Now since f is continuous, since f is continuous at C, so what will happen? There exists a neighborhood, a delta neighborhood, whatever, neighborhood U of C, such that for all x belongs to that neighborhood, you have f of x less than f of C plus epsilon and f of C minus epsilon less than this, correct. So now epsilon is what? Now f of C minus epsilon is same as f of C minus f of C minus 1, so this is 1. So hence f of x is greater than 1. Okay. So this is another way we can solve this problem. Is it clear how we got this answer? So here we are only using the fact that f is continuous at a particular point. Okay. Okay. Any question? Okay. Like because f of C is greater than 1, and now how it will be the it's a question of brain science, not the question of mathematics. How brain got that idea? Okay, so it's like her brain able to produce that. You have to consider that epsilon equals to this f of C minus 1. Okay. 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 Look at the question number 15. Prove that the functions f of x equals to 1 by x and gx equals to 1 by x are not uniformly continuous on 0, 1. Oh, you already solved this problem during lectures. Okay. Oh, okay. So someone raise your hand to please ask your question. Please ask your question. No, I think someone raised their hand. Now it's not. Yes. Any question from the online participant? Okay, let's continue. Okay, we have already solved question number some part of question number 15 where fx is 1 by x and gx is sin 1 by x. You have to consider suitable sequence and prove that that sequence is a Cauchy sequence, but not f of xn or g of xn are Cauchy sequence. Okay, is the function hx equals to x sin 1 by x is uniformly continuous on 0, 1? Are they Cauchy continuous on 0, 1? Okay. So we will try to solve the question, but before that, the hint is that try to solve question number 16. If you can solve question number 16, then you can solve question number 15. Let's say that question number 15 is true, 16 is true, try to solve question number 15 first. So what question number 16 says? A function f on open interval AB is uniformly continuous on open interval AB if and only if limit x tends to a plus fx and limit x tends to b minus fx both exist finitely. So now for this case, is it true? Okay, so if this right hand limit and left hand limit exist, then the function will be uniformly continuous on 0, 1. Okay. So question number 15. We are solving using question number 16. So we have fx equals to x sine 1 by x belongs to open 0 1. Now what about limit x tends to 0 plus x sine 1 by x? What is this limit? Is 0. Why? Is a bounded function, because x tends to 0 is 0 and sine 1 by x is a bounded function. Okay, so together it will be 0. So this limit exists, and limit x tends to 1, x sine 1 by x will definitely exist and it will be sine 1. So both limit exist. So therefore f is uniformly continuous on 0 1. Therefore f is uniformly continuous on 0 1. You may try to solve this problem using definition, but I think this is much suitable approach, that we can use this idea and solve it. So this is a uniformly continuous function. So 1 by x is not uniformly continuous, sine 1 by x is not uniformly continuous, but if you multiply x with sine 1 by x, it will be uniformly continuous on 0 1. Now the main question, how to solve question number 16. Is given that a function f is continuous on AB, you have to prove that it is uniformly continuous if and only if limit x tends to a plus fx and limit x tends to b minus fx both exist finitely. Okay, so go one by one. So question number 16. So first assume that limit x tends to a plus fx and limit x tends to b minus fx exist finitely. Okay, both exist finitely. What you have to show? To show that f is uniformly continuous on open interval a to b. Okay. How to approach? So somehow if you can get a function whose value is same as the value of f on the open interval ab, and that function is uniformly continuous on closed and bounded interval ab, then you are done. So try to find a function g which will be same as f, but that function will be uniformly continuous. Then you are done. Use the fact that both limit exist finitely. Define g equals to, okay, and g of a equals to, yes, correct. As we said, what you will going to do? You will define a function g of x equals to fx if x belongs to open interval ab, and g of a, she said something. Anyone else can guess? What should we define as g? Limit, correct, limit x tends to a plus f of x. This is well defined number, and g of b equals to limit x tends to b minus f of x. Now why g is uniformly continuous on. So you see that G is defined on closed and bounded interval AB. F was defined on open interval AB, but G is now defined on closed and bounded interval AB. Now how to show that G is uniformly continuous on closed and bounded interval? Yes. So if we can show that G is a continuous at the point A and B, then we are done. So now, is it continuous at the point A? Yes. Why? Because F and G are same over there. Okay. So G of A is defined as limit x tends to A plus fx. Now x tends to A plus means what? X is in a neighborhood of A, so it's the right hand side of A but not A. Okay. So that means you can fx and gx are same basically in this case. Okay. And therefore G is continuous. So this implies G is continuous at A, and G of B similarly, G of B is limit x tends to B minus fx. Again, x is a x are the points in the neighborhood of B but not B. So in this case limit x tends to B minus gx, and this will imply that, so implies G is continuous at B. Now all other points, because F and G are same, so G is continuous. So we prove that G is continuous on closed and bounded interval AB. Now because we know that a continuous function on closed and bounded interval is uniformly continuous, so therefore we can say that, so hence G is uniformly continuous on closed and bounded interval AB. So now if we have a function which is uniformly continuous on a set A, then it will be uniformly continuous on any non-empty subset of that set. Okay. So consequently G is uniformly continuous on open interval AB. Now in open interval AB, G and F are same, so thus F is uniformly continuous on open interval AB. Okay. This is the very simplest way you can prove that. Okay. So now converse part. What you have to do, you have to show that F is uniformly continuous on open and interval AB. You have to show that both limit x tends to A plus fx and limit x tends to B minus fx exist finitely. How to do it? So now converse part. Conversely, let F be uniformly continuous on open interval AB. What you have to do? We have to prove limit x tends to A plus fx and limit x tends to B minus fx exist finitely. Just try to show one, limit x tends to A plus fx exists. Similarly, you can prove that limit x tends to B minus fx will exist. Now how to approach? Okay, hence is that try to show that a sequence converges to a f of x will also converges to a. I mean f of a or some limit, or not f of a, some limit, not because it will be not exactly f of a, because f of a is not defined. Okay, are you getting it? What I am telling you to do? Suppose you have to show that this limit, let limit x tends to a plus fx equals to some number L. So this will be L. So try to find, so this will be L if and only if every sequence for every sequence xn converges to A, obviously xn is greater than A, f of xn converges to L. This is the sequential criteria of limit. If we can prove that xn converges to A where xn are greater than A, f of xn belongs to L. Okay. Let's say you have a sequence xn which is greater than A, or sequence from the open interval AB such that xn converges to A. Then what you can do? So let xn belongs to open interval AB and xn converges to, then what we can say? Yeah, it's uniformly continuous. So yes, Cauchy, because xn converges to A, so xn is a Cauchy sequence in open interval AB. Good. So then xn is a Cauchy sequence in AB, and since f is uniformly continuous on AB, what we can say, f of xn is Cauchy. So because it's a Cauchy sequence of real numbers, it will definitely converges to some number. Okay. So let f of xn converges to L. Are you, it's complete the proof, or we have to do something else? Is it the completion of the proof? Can we say that limit x tends to A plus fx will be L? No, we only prove that there is a, for a sequence xn, f of xn converges to L. But you have to show that whatever sequence you have converges to A, that sequence, f of that sequence converges to L. So let's say yn be another sequence converges to A. Okay. So let yn, because what happened, why we cannot be sure? Because maybe for yn the sequence converges to some other number m and L is not equals to m. Then the limit does not exist. So what you have to show that let even be a sequence from AB such that Yn converges to A. Okay. What you have to show? We have to show that f of Yn converges to L as well. Okay. So we have to show f of Yn converges to L. Okay. How to show that f of Yn converges to L? You can prove by contradiction or you can use different way to solve it. Yes, like we did in our one of our proof of a theorem. So we'll construct a new sequence. Yeah. So let Zn be a sorry, not Zn, defined basically. Define Zn as follows. Z of 2n is equals to xn and Z of 2n plus 1 equals to yn. Now both xn and yn converges to A, and obviously Zn is a sequence in open interval AB, and both xn and yn converges to A, so Zn converges to A, hence Zn is a Cauchy sequence, correct? So clearly Zn is Cauchy in AB, and since f is uniformly continuous, since f is uniformly continuous, f of Zn is Cauchy, but it is a Cauchy sequence of real number, so definitely it will converges to some number, but its even term converges to L. So like why? What is the even term? Xn, and we know that f of J2n is like nothing but f of xn, and f of xn converges to L. So it's definitely Zn converges to L, and hence the odd term like f of yn also going to converge to L. Okay. So therefore f of Zn is a convergence sequence since f of Z2n is f of xn converges to L. So what will happen? F of yn, which is f of Z2n plus 1, is also converges to L. So this proves limit x tends to a plus fx equals to, because whatever sequence you have, if it converges to the point A, then definitely f of the functional value of the sequence will converge to the number L. Similarly, you can prove that limit. Similarly, one can prove limit x tends to b minus fx exist finitely. Fine? Is it fine? So it's just a idea that, okay, so actually you see that instead of considering the function f is uniformly continuous, we can consider the function is Cauchy continuous. We did not use the full power of uniform continuity, we just use the power of Cauchy continuity. Okay, so that whole thing can be proved for a Cauchy continuous function. Okay, so obviously therefore x sin 1 by x will be Cauchy continuous. It's uniformly continuous, so therefore Cauchy continuous. Okay. So this is all, these are also conditions for a function to be Cauchy continuous. Okay. Another thing you observe that we have a function defined on open interval AB, and we construct a new function which is now defined on closed and bounded interval AB. So this type of thing we call is an extension of a function. So if we have a function, continuous function defined on open interval AB, and limit x tends to a plus fx and limit x tends to b minus fx both exist finitely, then we can extend the function, extend in a bigger set, correct? So like from open interval now we can extend the function to closed and bounded interval AB. So this is another problem in an actually in basic I mean in fact in topology, if we have a continuous function defined over a set or a subspace, we try to get a condition that will help us uh, to say that this function can be extended to a bigger space. Okay, one of the landmark theorem is Tejas extension theorem. Okay, you can extend a continuous function in closed subspace to a whole space. Okay, so anyway, that's another extension type of thing. Okay, look at the question number 17. Okay. Now instead of open interval you have left closed, right open, like closed 0 infinity is a continuous on days, and given that limit x tends to infinity fx is 0, prove that f is uniformly continuous on this set. Left close open. So if we have this, then f will be uniformly continuous on left close right open, I mean 0 comma infinity. Any idea how to approach? So use the facts. So question number what? 17, correct? What is given? Given that f is 1, f is, again same thing is happening, f is continuous on this set. Second, limit x tends to infinity fx equals to 0. Okay, what you have to show? To show f is uniformly continuous on 0 to infinity. Okay. So we'll use epsilon delta definition. In this case, we can't use any other definition. Okay. I mean, you can use, but we're going to use epsilon delta definition. We'll show that whatever epsilon we have, we'll have a delta for which x minus y less than delta will imply fx minus fy less than. Okay. So let epsilon greater than 0 be given. Okay. So since if limit x tends to infinity fx equals to 0, what will happen? So then since limit x tends to infinity fx equals to 0, what we can write? So there will exist a number, real number p, such that, so there exists a p obviously greater than 0 such that x greater than or equals to p mod of fx is less than epsilon. Later you might need to say that epsilon by 2 or something like that, but let's say it's epsilon. Okay, we'll later adjust, or if you want, we'll adjust it. Let's say epsilon by 2. So if you have a number x which is greater than or equals to p, then mod of fx will be less than epsilon by 2. So now we have a line, we have 0 somewhere in between p. So if you have a number over here, then the mod value of the function is less than epsilon by 2. That means function is bounded over there. Okay, that part. Okay, now in between 0 to p, look over here, if it's continuous on whole line, basically whole positive line, 0 to infinity. So therefore, so since f is continuous on 0 to infinity, it is continuous on closed 0 to p, closed p, correct? Now what? It is continuous on closed and bounded interval, so it will be uniformly continuous on closed and bounded interval. Okay, so then f is uniformly continuous on closed and bounded interval AB. So I am writing UC, short form of uniform continuous, because it's lengthy. That means what? That means thus there exists a delta 1 greater than 0 such that x y belongs to 0 to p and x minus y less than delta 1 imply that fx minus f of y is less than epsilon by 2. Okay, this is what, this is another thing. Good. We have to use one more tool. So like, okay, so why we have to use another tool, we'll see it later, but let's approach. Now approach, let's say we have 2 points. So now we have a point. So we have 0 to p and p to infinity. So if we have 2 points x and y whose length is less than delta 1, then obviously fx minus fy will be less than epsilon by 2. Let's say 2 points you have over here whose length is, now let's say you have 2 points over here, x and y. Okay. So if we have x, y only in these 2 in between 0 to p, then we are fine. So let's say you have x, y in between is greater than p. Okay. So if we have x comma y greater than p, okay, we have to think about p later, or p is also we have included. So greater than equals to p. Then what we have, f of and okay, and obviously we assume that x minus y is less than delta 1, let's say delta 1, something like that. Then f of x minus f of y is what? By triangle inequality, it is less than f of x plus f of y, and which is less than epsilon by 2, and we'll have less than epsilon. That's also fine. So you can use the same delta 1 and you have x minus y less than delta 1, then f of x minus f of y will be less than epsilon. So if we have both x and y inside this interval, then fine. If we have both x and y inside that interval, then also fine. Now the problem is that, let's say over here you have one x and y is over there. So now the third possibility, so let x y be such that x belongs to, let's say, 0 to p and y belongs to p to infinity. Then what you can do? We cannot do anything because we don't know what to use. So that means we have to consider the point P, so what we can do, like f of x minus f of p plus f of p minus f of y. Correct? We can use this fact, triangle inequality. If we can show this is less than epsilon, this is less than epsilon, then we are done. Okay. So now whatever p you are considering, that's important. If x minus p, you are not sure that whether x minus p will be less than delta 2 or not. Okay. So yeah, actually we are done basically. Is it? Okay, and obviously less than delta 1. So x minus y less than delta 1. So then x minus p will be less than delta 1 and p minus y also will be less than delta 1. Okay. So then, yeah, it's coming, correct? Yeah, it's coming. Basically, we don't need that. So less than epsilon by 2, because x minus p will be less than delta 1 and this is also will be less than, it will be less than epsilon. So little bit adjustment is needed. That's why you need to consider that f of p minus y should be less than epsilon by 2. Otherwise, you will have epsilon by 2 plus epsilon, because epsilon by 2 plus epsilon by 2. Okay. What you can do basically, you can adjust there, like epsilon by 3, epsilon by 3, something, or epsilon by 4, and from there ultimately you can do it. Okay. So let's say if you put epsilon by 2 over here, and then you'll have epsilon. Okay. So what you can do here, put epsilon by 4, epsilon by 2, which is less than epsilon. Okay. So that's how you can solve this problem. Okay. Anyway, this is the idea we are just using. Fine. If there is any flaw, please let me know. Okay. Don't fall into sleep. If you want to sleep, you can go outside and have a good nap. Oh, okay. So this is a question number 17. Question number 18. Show that every additive continuous function on R is uniformly continuous on R. So if we have additive continuous function, then it is definitely an uniformly continuous function. How to prove it? I think it is very simple. You try to prove it. I'll give you 5 minutes. It's a question number 18. So what is given? So given is that 1 f of x plus y is fx plus f of y. This is because f is additive. What is the second thing? F is continuous. What you have to prove? F is uniformly continuous on R. So same, that means if we have x for any given epsilon greater than 0, try to find the delta such that x minus y less than delta implies that fx minus f of y less than epsilon. What are the properties we know till now about additive function? Right, so already given, it's continuous on R. Yeah, f of 1 into x, okay. Yeah, then we are done basically. Yeah, correct. Yeah, but as he said that yesterday we proved that if we have an additive function and continuous on R, then it will be f of x is f of 1 into x. So what is that question number? Question number 5? Yeah. So f is continuous function on R and f is additive. If f of 1 is 1, then prove that f of x equals to x. But actually whatever f of 1 is equals to, let's say, k, then f of x will be k into x. If we look at the solution, so then what we have right now is very easy if we use that fact. What is now question number 18? Oh, sorry. So use problem number 5. Our fx will be k into x, where k is f of 1. Correct. Now it is very easy to show that it is uniformly continuous. How to show? So what will be our delta? So let epsilon greater than 0 be given. What should we choose as a delta? Choose delta f equals to, or it can be chosen like epsilon by k. Correct. F of 1 is okay. We also proved that f of 1 cannot be 0. That's also obvious. F of 1 plus 1 will be f of 1 plus f of 1, and we can prove that it should not be 0. Okay. Okay. Choose delta equals to epsilon by k. Then you have like x minus y if it is less than delta. This will imply that f of x minus f of y, which is kx minus k of y, is k into x minus y. Okay. So k into less than epsilon by k, because x minus y is less than delta. So we will have epsilon. Okay. So that's how we prove that. Okay. By the way, did we prove that f of 1 cannot be 0? Yeah, if f of 1 is 0, f will be 0 and everything will be, yes, okay, anything, whatever. Whatever f of 1, you will have the same thing. Yes, thank you. So it's obvious, very obvious if you have solved question number 5. Otherwise, you have to go through the same type of concept, I mean, same type of uh, procedure to get the solution, like as he said. So consider a sequence, something like that. Question number 19. So A be a non-empty subset of R, and you have a function defined by f of x equals to infimum of mod of x minus a belongs to A. So that means we are just calculating the distance of a point from the set A. Okay, if you look at the metric space, this is nothing but distance of x from the set A. That's a distance function. To prove that the distance function with respect to A is uniformly continuous or not. If you just look at the problem, it will not going to solve by its own way. You have to think about it. Try to write on a paper and try to solve it. So what you have to show? You have to, for a given epsilon, you have to find delta such that it will work. These are not that hard problem. It's a very, I mean, I will say they not easy, but medium type of problem. But they are really hard problem. It's a more or less okay problem. Okay, hence is, can you show that f of x1, f of x1 minus f of x2, the absolute value is less than equals to mod of x1 minus x2, or any constant into mod of x1 minus x2, like it's a Lipschitz type of function. Have you got it? Anything? Use the property of infimum. Okay. Question number 19, correct? So let x1, x2 be any two real number. Okay? Be any two real number. Then for any A belongs to A, we have x1 minus A can be written as x1 minus x2 plus x2 minus A, correct? This can be written as x1 minus x2 plus x2 minus A, correct? So now infimum of the set, so can you see this infimum like all x1 minus A such that A belongs to A, which is nothing but f of A x1 is obviously less than equals to mod of x1 minus A, this particular A, because this is an infimum, so infimum obviously less than of any element over here, correct? Infimum means the lower bound, this should be less than equals to any element, so x1 minus A, so therefore this is less than equals to, okay, you might change the notation, let's say this is A star because we choose A over there. So infimum of this less than this, so we have x1 minus x2 plus x2 minus A. Okay. And this is true for whatever A you have. Okay. So what we got? So we have f of A x2 less than equals to x1 minus x2 plus x2 minus A for all A belongs to A, because this A was arbitrary. So this is true for whatever A you have. Okay. Now that means what? If you consider, forget about this, then x2 minus A has a lower bound this set. Okay. So from there we can say that x1 minus x2, this value, okay, I should write other way, one more step. Oh. Minus x1 minus x2 is less than equals to x2 minus A for all A belongs to A. So that means this is a lower bound of the set of collection x2 minus A belongs to A, and infimum is the greatest lower bound. So therefore this implies that this is A x2. Did you get it? This part, whatever A you have this one. So that means A x2 A, this is a number, fixed number. This is the lower bound of the set. So what is the thing? This is your lower bound of the set. Which set? This is a set. Let me write x2 minus A such that A belongs to A. This set has a lower bound, this one. So now infimum of this obviously going to be greater than the lower bound, correct? So therefore this is nothing but the infimum. Okay. So therefore this is less than this, and this proves that f of A x2, sorry, I think I missed A, this should be x1. x1 minus f of x2 is less than equals to x1 minus x2. Is it clear? Now similarly you just interchange the role of x1 and x2, you'll have the mod value. Okay. So ultimately what we got consequently, if we change the role of x1 and x2, we have mod of f of a x1 minus f of a x2 is less than equals to mod of x1 minus x2. Now what? Now it's very simple. Whatever epsilon you have, choose delta equals to epsilon, you are done. Okay. So this is the thing you have to prove. Okay. So what we prove? We prove that distance function with respect to A is a uniformly continuous function on the whole line. Okay. Is it clear? Any question? Any question from online participant? Okay, I think. Okay, question number 20. Show that for given any non-empty closed subset A of R, there exists an uniformly continuous function f on R such that f of A is equals to 0. So this is, you have to find, so whatever non-empty closed set will be given to you, you need to find a function f such that all f of A is equals to 0. Okay. Actually, you need to find a function f whose 0 set, that means collection of all x where function vanishes, is same as the set A. Okay. The hint is that the function will be f of A. The function given in question number 19, but why? It will be 0. The 0 set. Whatever element you will choose from the set A, f of A will be 0. You have to find such a function. Okay, I think it's non-zero uniformly continuous function you need to find. Otherwise, 0 function is satisfying this property. Okay, or the question is that it's 0 only at A, no other point. So let me modify the question. So that for any given non-empty closed subset of R, there is an uniformly continuous function f of R such that the 0 state of the function f is the non-empty closed set A. Okay. By the way, it's a simple result, although we did not include in the proof. That's coming from question number 12, I guess. The set of zeros of a given function is a closed set. Because fx equals to gx is a closed set, take gx is a 0. So the collection of all points where fx equals to 0, that set is a closed set. Okay. So that's the thing. The hint is that try to take use question number 19 to solve question number 20. One part is easy, correct? Okay, let me give you what are the information we have till now. So from problem 12, we know that the set Z of f where all x belongs to R such that fx equals to 0 is a closed set. Obviously, f of A is 0 where f of a is a continuous function. We already proved it's a uniformly continuous function. Okay. Is a closed set. Correct. So from problem number 19, we know that f of a of x, which is infimum of mod of x minus a such that a belongs to a, is uniformly continuous on whole real line. Now, if we have a x as an element of the set A, so obviously f of a is what? 0, because what will be the infimum distance? That's it's obviously going to be 0, correct? So clearly A is a subset of Z of f. That part is okay. Now we have to prove that Z of f equals to A. So so whatever point you will choose from there, that will be inside the set A. Okay. So we have to show that ZF subset of A. Okay, so then we are done basically. Correct. Oh, F of A basically. How to show that Z of A is a subset of A? Take a point from that set. Okay. So let X belongs to this set. Then what will happen? Then f of a of x is 0. Okay. That means what? Infimum of the set is 0. So that means whatever the positive epsilon you will choose, okay. So then, no, that is infimum of the set x minus a such that a belongs to a is 0. Then for any epsilon greater than 0, what will happen? By the property of infimum, there will exist an element from A such that that will be less than epsilon. Okay. So by the property of infimum, okay, what it is? By the property of infimum of a set, there exists an element, let's say A star belongs to A, such that x minus A star is less than epsilon. That means what? It means that epsilon neighborhood, any epsilon neighborhood of the point x, so this means any epsilon neighborhood of x contains a point of A other than If you have a question, you can unmute and ask. Please unmute yourself and ask. Dr. Babulal, do you have any questions, sir? Okay, I think mistakenly raised. It contains a point of A other than X. So that means what? Actually, you don't need just a point other than X is not needed. We don't have to bother about whether it contains any other point or not. We just need it contains a point of A. That's enough. Because we are not sure that it will contain other. What happened? Contains a point of A. That means what? Does X belongs to A closure? Correct. So we prove that whatever neighborhood of the point X, it will always going to contain a point of the set A. So that means X is an element of closure. Okay. So this proves, but A closure is A because A is a closed set. So thus X belongs to A. Hence JRF equals to A. Actually, in general, the zero set of a function is basically, so in this case, like JRF of A. So if A is not a closed set, JRF of A is nothing but is closure. Can you see that? So if A is a closed set, then JF of A is A. In general, if F is not closed, in the question, if A is not closed, then we have this ZF of A is nothing but A closure. One part you can see that ZF of A is a subset of A closure is fine. But what about the other part? We prove that A is a subset of ZF of A. Then how can we say that A closure will be over here? Yes, A closure is the smallest closed set and Z of A containing A, and ZF of A is a closed set containing A. So therefore A closure is a subset of ZF of A. Good. So that's how we can actually prove that this is true in general. Okay. Even if A is not a closed set. Okay. I think that's all for today because it's a 3:30, is that correct? Okay. Tomorrow we'll continue from question number 21. Or actually, if you try to practice question number 21, 22, 23, it's like you have to use intermediate value theorem to prove all these questions. Try to solve it because let's see whether we can consider this question in the next class, because next class tomorrow we'll start with the types of discontinuity of a given function. So we'll spend some time on. Okay. Any question from online as well as offline? No. Then we are concluding this session. Mm-hmm. We'll again meet after 15 minutes. There is a little bit break.
Hello. We'll do some of the tutorial problems from yesterday and some of the new problems. Before that, let me correct the mistake which some of you pointed out. This is not injective in general. By mistake, I said this is in general not injective. Okay, this F star is not in general injective. When is it injective? When n is equal to kernel of F. Okay, it's injective if n is equal to kernel of F. Okay, that means yeah, H. In that case, H will be, I mean, image of F will be isomorphic to G mod n. Okay. Okay, fine. So continue. Tutorial problems from yesterday. Some were remaining. Okay. Actually, can you turn on hotspot once more? I need to share it. Yesterday's. Sorry, one moment. One. Yes. Done. Yeah. Sorry. Let's see. Interesting. Okay, one of the problems from yesterday. If H and K are finite subgroups of a group G. Okay, so this is problem 2E from day 1. Problem 2E. H and K are finite subgroups of a group G. Okay. Then what is the cardinality of the set HK? Or in fact, the expression is given, you just have to prove that that is a cardinality. Anyone has any idea? You have to prove that this is equal to something, whatever is given. Anyway, without thinking of the RHS, just from scratch, how do you prove it? Of course, looking at the RHS actually helps you to think of what you need to do. Okay, I'll show you different way of writing it, but okay. Let's say H is equal to x1, etc. What did you say? Xn? Xn. Okay. Oh, not done. Okay, fine. G? K. Okay. Huh. Oh, I see. Okay. Okay, fine. Xi's are there in both. Okay. Okay, so now if you take HK, let's see. What will be the elements of HK? You will have, I'll write in general form. You will have elements of the form Xi, Xj. This is not how I would write it, but we'll try it this way. So you would have elements of the form Xi, Xj for I and j between 1 and n. Then also elements of the form Xi, Li, Lj, or maybe I should write Lt because different range for j, right? And also G U Xj. Okay. And finally Gu Lt. Okay. For the respective ranges. So I'm just writing in general. Okay. Then what? What you need to count is the cardinality of Hk. So why is it not equal to cardinality of H into cardinality of K? Intersection? Can you make that clearer? Hmm. So what? Intersection? Hmm. Yeah. X1 will appear only. If you write it in that form, X1 will appear only once. Because you have to take H and then K in that order. H1 K1 may be equal to H2 K2, right? You understand this intuitively, but you have to formalize what that means. You definitely know why it is not always equal to cardinality of H into cardinality of K. Yeah, so the possibility is some of the elements may repeat when you write this as a list. If you list all these elements, they may be, some of them may be the same, correct? Okay, so if you write it this way, how will you yeah, this way you can argue this way. So if you write it this way, then how will you argue that you only need, well, the other problem is if you look at the expression, it is not something like cardinality of H plus cardinality of K minus cardinality of H. In that case, you can say that I need these elements, these are over counted, so let's subtract. But it is not subtraction. It's actually a very similar expression, but multiplicative, correct? Instead of adding and then subtracting, adding two things and subtracting the intersection, you're multiplying them and dividing by the intersection. So when will that happen actually? When will you divide by something when counting something? In general, in combinatorics, I mean, generally speaking, when will the division come up instead of subtraction? Subtraction is an overcounting of a particular form. When you have this many elements which have been counted twice, then you subtract them once. Another form of overcounting leads to division. When? Combination. Okay. That is one example. NCR, for example. Why is there division in that? Repetition is there in both. Overcounting means repetition, but what form of repetition? Yes. Some set, uh, not some set, but a set of a particular cardinality is appearing so many times. Okay. Or in other words, there are some number of elements that are equivalent to one another in some sense. As far as we are concerned, they are equal. Okay. So in this case, they are literally equal. Some of these, that's what we said. Some H1 K1 may be equal to H2 K2. Okay. So if I write cardinality of H times cardinality of K, this correctly counts something. Which thing? This is the correct cardinality of one particular set. Which set? Cartesian product. This is indeed the cardinality of H cross K. Okay, because there is no question of repeating things. H1 K1 as an ordered pair is not equal to H2 K2 unless H1 equal to H2 and K1 equal to K2. So in that case, there is no danger of repetition or overcounting. But here, since we are applying the group operation, we may get some elements are equal like this. Okay. So now you know what to eliminate and how to eliminate, meaning you're dividing because when you consider this, many of them are equal, but in a uniform way. Uniform meaning what he said, that the number of repetitions will be in some sense the same. Okay. Differences of repeated elements will be there in that list. Okay. With the same number of repetitions within that class. That's why we are dividing. So here, can you see which of them may be equal? I think even if you write it this way, it is not very clear. I don't think it helps because my general argument is different. I don't explicitly list the elements. I just make a general argument by observing the set. Okay, but if you list it this way, I thought that this might actually help because here definitely you have elements which are there in both H and K. Can you say the other elements are not? For example, these elements. Yeah, those elements are definitely not there in the intersection, correct? Because you know that by assumption that these LTs are not there in H, but they are in K. But XIs are there in both H and K. So if the product is there, for example, in K, then sorry, this is there in K, but not H. This is there in K, not H. Similarly, this is there in H, not K. Right? And yeah, this cannot be there in either. Yeah, this cannot be there in either. Yes. Here, no. All four individually need not belong to the intersection. That's not true. Individually, no. Okay, I'll tell you the simple counterexample. HK is equal to HK. Is that true? Yes. Does that imply that HK are, I mean, H comma K comma H comma K, that is H comma K, they are all in intersection? If this argument is true for any H1 K1 H2 K2, then it should be particularly true when H1 is equal to H2 and K1 equal to K2. But that would be absurd because you're implying that whenever HK is equal to HK, which always is the case, H and K both belong to H intersection, which is not true. This can be true for anything, right? So that cannot be the argument. Okay. Anyone? Any idea with this in Cartesian product? Okay, fine. So I'll take you halfway, then you can tell me. Consider H cross K. Okay. Define a relation on, yes, function also you can define, that's another way. But I will define an equivalence relation, in fact, a relation on H cross K as follows. H1 K1 is equivalent to H2 K2 if this holds. H1 times K1 equal to H2 times K2. Is it an equivalence relation? Yes. I mean, if you have done quotient fields in ring theory, basically it's very similar. That's slightly different. There's cross multiplication, but it's very similar. Okay. Okay. Actually, this is simpler than that. This is simpler than that because obviously it is reflexive. HK is equal to HK. Okay. Symmetric, obvious. Transitive is also obvious because you don't even have to cross multiply. thinking of quotient field. If you have further H3K3, then H2K2 equal to H3K3. Suppose this is equal to this and this is equal to this, then equality is transitive. So immediately you get H1K1 equal to H3K3. So if you add this part, then you further get. So these two are equivalent, I mean equal. Therefore, this is equivalent. Yeah, I mean this is equivalent to this. Correct. So that follows immediately. Transitivity. This obviously is an equivalence relation. So now, can you tell me what we are trying to count in terms of this? In terms of H cross K, what are we trying to count? The classes, right? In HK, we are trying to count the distinct elements, but those distinct elements means you want to count how many H1 comma K1 are there, such that H1, how to phrase it? You want to count elements of the form HK in HK, but without repetition. Without repetition means if it happens that H1K1 is equal to H2K2 for some H1, H2 and K1, K2, then you want to count these two as one, right? So you want to count this pair as one. You don't want to count them as two different things. You want to count them as one. That means the equivalence class of any HIKI in this relation, you will count that class only. You will not count each element in that class. You will just count that class. Okay. So now the question reduces to how many equivalence classes are there. Okay. So then the question is, when will these two elements be, I mean, when will these two pairs be equivalent? Like, what is the alternative way of writing this? So how else can you write this? By rearranging. Now you can do that rearrangement. So actually you are almost there. But you mistakenly said all four are there. That is not true. What is there? H1 K1 equal to H2 K2 implies if you multiply by H2 inverse and K1 inverse, let's say like this, H2 inverse H1 equal to K2 K1 inverse. Be careful of the sides on which you are multiplying, because H2 is here. If you transfer it here, it will be on the left, and K1 then if you transfer it here, it will be on the right as inverse. Okay. H2 inverse H1 is equal to K2 inverse K1. Okay. But that means we know that this element is where definitely in H. And this element is definitely where in K. But if they are equal, that means this is there in HK. So this belongs to HK. But then, yeah, if you take a pair HK, can you tell me how many elements will be there in its equivalence class? This is one observation. That is okay. But then going back from this, can you tell me what is the, can you tell me an arbitrary element which will be there in this equivalence class? The form of an arbitrary element, which if I write, then immediately you know that it's there in the equivalence class. Instead of writing some H prime, K prime, and then writing this condition, what is a way to directly write something, some more complex expression, something comma something, such that it's obviously in the equivalence class? Or can you tell me something else where if I multiply these two, I will get K? What is one easy way of ensuring that? One is to write H comma K. Another way, I should take, so I'll write something here. I'll write this as X. Okay. So I want XY to be equal to HK. but x and y should be in terms of h and k and maybe something else. What is it that I can write so that when you multiply, immediately you get hk? H into something, h into some g, and g inverse into k. Correct. Any element of this form is in this equivalence class. That is true. How many elements of this form will be there? For all g, will it be true? Yeah. But if you now use this condition, you can say that g should be what? Huh? To get distinct, actually, yeah. To get the distinct elements, I need this one, right? What? Right. Yes. So H2 inverse H1 belongs to H intersection K. Correct. That is H2 here. So that means G inverse belongs to H intersection K. That means G belongs to H intersection K. Yes. No. I think I don't know. Sorry. What? Uh, oh, right. Sorry. Obviously H intersection. I meant H intersection K because I'm saying it's there in H and K. Okay. Yeah. H intersection K, not HK. Sorry about that. It is there in H intersection. That's all. Did I do the multiplication H2 inverse and K2? Correct. That is correct. G inverse H inverse H. K2 K inverse K1 inverse. That will also give me G inverse. Yes. Okay. Yeah. So why is it true that otherwise also why is it true that G should be in H intersection K? I mean, even if I write an arbitrary G, this is true, right? Why do I need G in H intersection K? This should be in H and this should be in K. So equally, either you can do this or directly from this. If you write that also, you will get G is in H intersection K. So the elements in this equivalence class are exactly these. I can take all the elements of H intersection K and get this. Are they all distinct elements? That is corresponding to distinct elements of H intersection K. Do I get distinct elements here? By cancellation, you have to get no. If you change G, H is same. You're taking one element from this equivalence class and trying to generate all the others. Do you understand what is going on? I'll write this again. If you take one element, I know that there is some equivalence class here. So actually, if you take H Cartesian product with K, just as sets, we're not doing root direct product or anything. Just as sets, if you take, then I know that there are some other, say, HG1, G1 inverse K, HG2, G2 inverse K, etc. Okay. And similarly here, whatever. Okay. So I am trying to count these equivalence classes. Okay. Instead of the individual elements. So I want to know how many elements are there in an equivalence class. So firstly, we determine that we need G in the intersection then I can do this. So here G1, G2, etc. whatever are in the intersection. Okay, and of course E is also there. For I can write this itself as HE comma EK, right? Where E is there. So that also conforms to that. Okay. So now the question is, are these all distinct if I take distinct elements of H intersection K? If I take distinct elements of H intersection K, Gi, distinct elements of H intersection K, then because cancellation, you can apply cancellation on either component. If H G1 equal to H G2, for two of them to be equal, each component has to be equal. Even if one component, even if first component is equal, then by cancellation you get G1 equal to G2. Okay. So definitely they are distinct. So if I count how many elements are there in H intersection K, I am counting how many elements are there in one equivalence class. Therefore, and then all the equivalence class satisfy the same property, right? So therefore, the number of equivalence classes is the total number of elements in H cross K divided by number of elements in each equivalence class. But the numerator is clearly HK. Clear? Actually, this sort of counting argument appears in many other places also. It's a general, yes. Yes. If you want to do it the other way. Okay, if G is abelian, then yes. So then you're considering, yeah, let's try this way. So suppose G is abelian, or at least H and K are abelian. So then H cross K is a direct product of groups, considered as a direct, anyway it's direct product. Okay, here you consider as a direct product. Then, okay. So then actually you are only assuming that HK is a subgroup. You just need that HK is a subgroup because you are not doing to G. So it's enough for HK to be a subgroup. Yeah, suppose HK is a subgroup. So in that special case, you have a different proof. Let's see. So defining homomorphism from, yeah, good way. Yes. Then, f of h1 comma k1. Oh, right. Okay. I thought you are going for the equality condition. Yes. I assume that that is the mapping. Yes. Then you are looking at homomorphism. Yes. It is onto. Yes. Yes. Correct. So kernel of f will be what? Yes. So this is yes. Yes. Okay. Hmm. 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 H comma H inverse. So this is therefore equivalent to, I'll write instead of H comma H inverse, I'll write, what's the good notation? Okay, fine. X comma X inverse, where X belongs to H intersection K. Yeah, because this is equivalent, I mean, This is the same number of elements as H intersection. The second component is not free. It is determined by the first one. Right. So this one has cardinality. So this implies cardinality of or order of kernel of F is equal to order of, and so then it follows. Correct. When it is a subgroup, you can use that argument. That is true. So basically, it's the same idea, but that you are not using that it's a subgroup. Okay. Yeah, of course, you cannot use the first homomorphism theorem as it is. So actually, for category theorem, so you can think of this. The first isomorphism theorem, right? You study it in group theory, ring theory, generally in universal algebra. More generally, it holds in any kind of setting, basically. So in set theory itself, this is there. In set theory, how will you state first isomorphism theorem? So if f is a function from a set S to a set T, then I want to be able to say that S modulo kernel of F is isomorphic to image F. But it's just a function. S and T are just sets. How can that make sense? That is a question. What is kernel? Kernel in general is an equivalence relation. It is only in some special algebraic structures like groups and rings and vector spaces that the kernel is defined as just a special sub-object. Okay, a normal subgroup in groups, ideal in this one, any subspace in vector space. But actually kernel is what? So if you have S and T, observe that these three elements are mapped to the same element. These two elements are mapped to the same element. And this element is, wait, what did I do? Oh, sorry, I made a mistake. Right, these two elements are mapped to the same element, and this one is okay. So it's a partition. That means if I consider the set of pre-images of set of pre-images of the elements of T, elements of image, because I don't want empty set here. If I take some arbitrary element, I make it empty pre-image. So of the image, then that partitions S. Is that correct? It has to partition S. Or in general, I can say define an equivalence relation on S as follows: S1 is equivalent to S2 if and only if their image is the same. Okay. F of S1 is equal to F of S2. That is an equivalence relation. Again, very simply. Actually, but it is a special case of this. That's what I'm building to. Okay. So this is an equivalence relation. This relation is equivalent to the partition, because you know equivalence relations are equivalent, same as partitions basically. So now the quotient of a set with respect to an equivalence relation is just a set consisting of the equivalence classes. Actually, that's it. It's just, I will use this notation for equivalence class. Okay. The set of equivalence classes is the quotient. You define it as that. So this is not quotienting with respect to a particular sub-object. It is quotienting with respect to an equivalence relation or partition. Okay. Then observe that do you have a natural surjection from S to this? So this is the quotient. Do you have a natural surjection from this to this? S to this? Yes. You can map these three elements to their class, this element to this class, its class, and these two elements to its class. So basically, S maps to class of S. It's well defined because we are not using representatives. Okay. Then what is the next thing I can do here? How do I connect everything? Define a mapping from S mod tilde to T. How? Here I see that all the elements in this class are going to this green point. Yeah, actually I should not say this because online people cannot see. Sorry. So all the elements in the green class are going to the green point in the quotient. So I map that. Yeah, map that to image of that class. It's well defined because by definition they are equivalent if and only if they have the same image, right? Similarly, this one, red one, gets mapped to this, and cyan one gets mapped to that. Okay. So this is, let's say, F star, and this surjection is phi. Observe that F is equal to F star after phi. Okay. And what else? F star is an injection because the multiple elements that are getting mapped to the same element, multiple elements of S that are getting mapped to the same element of T have now been merged into one element, and that one element we are mapping. So no two different elements in S in the quotient can map to the same element of T because they come from different equivalence classes. So they by definition get mapped to different elements, right? Yeah. So our mapping here F star is class of S gets mapped to F of S, which is well defined because of the way the equivalence is defined. Okay. And this F star is injective and its image is image F. Therefore, it is a bijection from this to so F star is a bijection from what? Quotient to the image. Therefore, the quotient is isomorphic to image. That is your first isomorphism theorem. So you can do that in a set. Similarly, you can do that in graphs, topological spaces, and so on. Topology also there is quotient space. Same idea. Okay. There also quotient space is not. So in topology also, quotient space is not something you define with respect to one subobject like that. You need to identify different points of the space together, and that gives you the quotient, right? Yes. No, we don't need injectivity because first isomorphism theorem is whatever be the homomorphism from G to H, G mod kernel F is isomorphic to image F. Which one are you talking about? Injectivity of? For this injectivity is not there. No. This is in general true for any. When it is injective, you get G is isomorphic to image F. Because if it's injective, kernel of F is trivial. So you will get G is isomorphic to image F. That will be an embedding. In fact, that's what you say that the homomorphism is an embedding if it is injective because it embeds G into H. Meaning you will get the image will be a copy of G. It will be isomorphic to G. It's a copy of G as a subgroup of H. Okay, so in fact, you think of subgroups as injective mappings only, injective homomorphisms only. Okay, yeah. So now, can you relate what we did earlier and what we are doing here with the first isomorphism theorem? So even if you don't have HK as a subgroup, this argument is not completely wrong. It's not that you are using first isomorphism theorems of groups. You are using first isomorphism theorems of sets. Okay, only thing is again, kernel F, only thing is it's not that easy. Kernel F is not the set. It is that equivalence relation which we defined. That is kernel F. But it is basically, so in the special case, the kernel F is completely determined by the set. That is the thing. Okay, actually, it's too much on one problem. Yeah, I will define group action. Okay. Oh, okay. Before that, I see another problem which we can do, which is problem 5. So well-known result. G mod Z of G is cyclic, but very useful for especially for problem solving many times. G mod is Z of G. Z of G is what? Center of G, set of all elements that commute with all the elements. G mod Z of G is cyclic, then G is abelian. Okay. Somewhat anticlimactic because if G is abelian, then what is G mod Z of G? It's trivial. So although you're saying cyclic, actually it is trivial. Of course, if you say that it is trivial, then there is nothing to prove. The point is another way to state, a clearer way to state, because this is misleading. You're saying that it's some cyclic group. You're saying it cannot be a non-trivial cyclic group. The different way of saying it is G mod Z of G is never a non-trivial cyclic group. Okay, that is one way to say it. Okay, how do you prove this? So, okay, first of all, G mod Z of G cyclic means what? It is generated by sum. So, I'll just take Z equal to Z of G. Okay. So, G mod Z of G looks like this. Okay, that means okay, maybe I should not have used capital Z, but hopefully you can distinguish between the different Z's. So, this is the structure of G mod Z of G. So, that is definitely abelian because it's cyclic. But you need to prove G itself is cyclic. So, you need to prove somehow that X and Y are in G, then XY is equal to YX. How to do this? What do you know from the fact that this is cyclic? Let me not use X and Y, I'll use A and B because X is fixed there. Okay, as that particular thing which generates. So I'll use AB. Don't use X again. X is that particular element. Okay. AB. Okay. So it is true that ABZ is equal to, not like that. It is true that AZ BZ is equal to BZ AZ. Okay. Since Z is normal, we can write that as ABZ is equal to BAZ. Okay. Then so when is it true that some AB belongs to Z? You are using additive notation. I will continue with multiplicative notation. So AB inverse BA, or AB if you prefer AB B inverse. Right. AB B inverse belongs to Z. That means AB A inverse B inverse equal to some small z in Z. Okay, in terms of elements. Then first of all, let's pause 1 minute. Can this line of proof without any further consideration work? Why? Yeah, we have not used cyclic. We have only said it is abelian. Cyclic implies abelian is true. But if it were true with abelian, then the question would have been, of course, it could be a trick question. But the question would have been that if it is abelian, then prove that, which is not true anyway. Okay. When you quotient by the center, for example, P4, triangle group of order 8, quotiented by its center, which is 1 comma r square, is abelian. You don't have to think of what group it is. It's order 4. Order 4 means abelian, right? In fact, it's Klein 4 group, but it is definitely abelian. You can also take Q8 instead. Okay, Q8 quotiented by its center, which is 1 minus 1. Again, it's order 4. In fact, it's Klein 4 group. It is abelian, but that doesn't make these groups abelian. So it cannot be true if you replace cyclic with abelian. Cyclic is needed. So you have to use that the fact that it is cyclic. So fine, this okay. In addition to this, what can you use? This much is true. You don't have to change that. You can go ahead with this if you use the extra information. A is equal to, since A is in some x power k, that xz power k means x power kz, correct? And B is equal to what? Oh, B is equal to belongs to, correct. B belongs to some x power L z, but that means A is equal to x power k z1, B is equal to x power L z2, where z1 and z2 belong to capital Z. Yes. Oh, right. I'm sorry. This, yeah. But, oh, that's the same thing though, isn't it? Yeah, it is the same thing. A belongs to A root, not A equal to A. Yeah. That's all. AZ is equal to some x power kz, which means A belongs to. When will two cosets be equal? When this times that inverse is there and so on. Equivalently, yeah. Yeah, or equivalently, this is in that coset. That's it. Okay. So yeah, I can definitely write this. I mean, maybe there's one trivial step missing there, but yeah. Okay, so then use that fact. Now what do you get? A and B are of this form, no? So what do you get from here? Yeah, in fact, I didn't have to use this part. I can just consider A inverse, B inverse. That's enough. Okay. Anyway, let's go ahead. Is that correct? This is equal to this, correct? A inverse, B inverse is equal to this thing. Now, what is this equal to? Fine. Can I cancel anything from here? Remember, Z1 and Z2 are in the center, which means what? they commute with everything. You can, in a product, in a word means if you write a string of elements of G, then the elements of Z can be moved anywhere without changing the value of the product. Okay, so without writing the step, this Z1 can be moved here if I want and then cancelled with Z1 inverse. Similarly, Z2 can be moved here and then cancelled. Okay, once you do that, what remains? Different powers of X, which anyway commute with each other, right? Powers of X will commute with each other, and you have power K, power minus K, power L, power minus L. So these all cancel out and you get E. So if A, B, A inverse, B inverse equal to E, that means AB is equal to BA. The commutator of A and B is equal to E means A and B commute with each other. Is it clear? Okay. That's it. Yeah, actually you can just start by considering. You don't need this part. Okay. You can just start by considering what is ABBA. Yeah. But even if you do this way, then you can pause at that point and say that, yeah, I have not used complete information. Any other? Yes. Okay. You want to show Z of G equal to, which is of course true ultimately. Yes. So you're assuming it's finite. Okay. So it's generally true. Okay. Not just for finite groups, but okay, fine. Let's assume this is of order n. Fine. Hmm. So yes. Correct. G power n belongs to Z of G. Yes. Okay. That is not true. That is not true. Power n belongs to that doesn't mean. Okay. That is not true. G power n belongs to Z is true. That doesn't. So, in fact, there is an earlier question where okay, I can't find the question here. It's there somewhere. Anyway, the question was if H is a subgroup of G of an abelian group G, okay, abelian group G, then you define a subset of this form. I mean, group of this subset of this form. And show that it is a subgroup. Question is, H is some subgroup of an abelian group G. Define subset X belongs to G such that X power n is in H for a fixed n. Okay. For a fixed n. Show that K is a subgroup. It's somewhat easy to do using the subgroup condition. But the point is that this will not be equal to H. If your argument was correct, then this would be equal to H itself. But that is not true. For example, I can take n to be order of G itself. Then X power n would be equal to trivial, I mean, identity element, which means it's always in trivial subgroup. But that would mean that every element of G is identity, or it's G is contained in the trivial subgroup, which is not true. So no, that cannot work. Okay. Yeah, correct. But what? Oh, okay. Okay, fine. Are you familiar with the quaternion group? I mean, all of you? All of you familiar with the quaternion group? You can define it in many ways, but one simple way is take the elements plus or minus 1, plus or minus I, plus or minus j, plus or minus k, where I, j, k are considered to be square roots of minus 1, but not the same element, just distinct elements. Okay, just for just algebraically, you're not considering it as really distinct roots or anything. Then you define ij is equal to k, jk is equal to I, kj is equal to, sorry, ki is equal to j. Kj would be equal to minus. So ki is equal to j, and ijk equal to minus 1. That's a simpler way of, I mean, more concise way of writing. But then from that you can get the implication that ji is equal to minus k, jk is equal to minus I, ik is equal to minus j. Okay, so yeah, and other one statements here is I square equal to j square equal to k square equal to minus 1. Okay. Then what is z? I said that earlier also. Z of Q8 is 1 comma minus 1. Now, for all x in Q8, x square is in the center, but the group is not equal to its center. Okay. So unless we use that, yeah. Here, of course, it is not true that n is the order of the quotient. Order of the quotient is 4, not that. But in fact, the exponent of the quotient is 4. Exponent means in the quotient, every square is equal to identity element. Because of this only. Okay. Quotient is Klein 4 group. So every element is self-inverse. So any element square is 1. Okay. So unless you use the fact somehow, in addition to this, that n is in fact the order of the quotient, at least that might work. I don't know. I've not seen a proof of that sort. Maybe if you additionally use the fact that n is the order, maybe it will work, because at least in this counter example, that is not the case, right? So, but still, I'm not convinced. That also may not be sufficient. I'm not really sure about that. Huh? That is true. Oh yeah, correct. Yeah, yeah. It is not that you have to take the minimal one. Yes, maybe you have to take smallest such n or something. But no, I don't think. Let's see. At least this is not enough. Okay, maybe you can modify it and get proof. Okay, let's go to another question. Yeah, next question. Question 6. Question 6 is prove that any group of order p square is abelian. Oh, that requires something else which I've not done yet. Yeah, that requires one more thing which I have not yet done. So I will very quickly do group actions, maybe using problem 9. Okay. So for this, I just need to basically define group actions. Again, you're familiar with this. So we say that a group G acts on a set X if there is a mapping, say phi, from G cross X to X, which takes. So we just write phi of gx. Instead, we choose to write it as g dot x. It is not the multiplication of the group at all. because X is some set. It is not. Okay, it is nothing to do with G. Means it is not made up of group elements or something. It is just any set. Okay, so we say that G acts on X if there is such a mapping satisfying the following properties. First property is that 1 dot X is equal to X, or E dot X is equal to X for all X. I'll try to refer to the elements of capital X as points and group elements as elements. Okay, so it is acting on a set of points. Think of it like that. Very common examples are geometric. So you really have points. So 1 dot X equal to X for any point X, and so if you take H dot X, that is another element of X. So again, I can use G on that. So G dot H dot X should be equal to G H dot X. Okay. Makes sense? This dot is the group action. H is the group operation, the multiplication in the group. Okay, so they are distinct things. They're not by definition, means simply they're not equal. You have to insist that they're equal. Okay, so this is, then you say that G acts on X. Specifically, it's a left group action. Okay, you can similarly define right group action. We look at left group action. Okay. Then, as soon as you define this, we have some definitions associated with this. So if you take X, if you fix X in X, the orbit of X is equal to G dot X for G belonging to G, and stabilizer of X is equal to G in G such that G dot X is equal to X. Okay, it's called the orbit because it's like an orbit, like you're thinking of it as action. So it is like the planets under the action of gravity follow a particular path. So if you take all the positions where it can be, where the planet can be, that is like the orbit. Okay, so it is like under the action of G. So for example, if I take S3 acting on let's say 1, 2, 3, 4, 5, 6. How can S3 act on 1, 2, 3, 4, 5, 6? It not naturally it acts on 1, 2, 3. I can make it act on 1, 2, 3, 4, 5, 6 also. In what way? I will say that if you take R of 1 is equal to 2, R of 2 is equal to 3, R of 3 is equal to 1, but also similarly R of 4 is equal to 5, R of 5 is equal to 6, R of 6 is equal to 4. Okay. So whatever the elements of S3 do on 1, 2, 3, I'll copy that to 4, 5, 6. Just to get a non-trivial example. Okay, I'll copy that to 4, 5, 6. You understand what I mean? I'm not writing it fully. So same thing, replace 1, 2, 3 by 4, 5, 6 and do the same thing. Where you have the elements S3 are, when we use the notation we used earlier. Okay, the dihedral group D3 notation. So this one. So then one can go to which all elements? It can go to 2 clearly. Can it also go to 3? Yes, in fact 2 can go to 3. So if 1 can go to 2 and 2 can go to 3, then that because of this thing, if I apply that group element which maps 1 to 2 and then that element which maps 2 to 3, the product of those two elements in the group has to map 1 to 3. So 1 will ultimately go to 3. Basically, R square of 1 is what? 3. That's all we are saying. R of 1 is 2. R of 2 is 3. Therefore, R square of 1 is 3. Okay. So 1 goes to 3 also, and then 3 also goes to 1 already. Okay. So that is the orbit of 1. Does R go to 4? By the definition I gave, you're only supposed to copy this action to 4, 5, 6. So separately. 1, 2, 3, and 4, 5, 6 separate. So 4 goes to 5 and 6. Similarly, 5 goes to 6 and 4. Okay, in fact, I'm not writing the complete thing. This is the orbit. Okay, so it is really like orbit. These 3 elements are in one orbit. Okay, these 3 elements are in another orbit of this action. Okay. Now, what is stabilizer? What is stabilizer of 1? Nothing. I mean, no, not nothing. Stabilizer of 1 is E, ID. Okay, maybe I'll write ID here. Okay, because 1 is there. So ID stabilizes 1 definitely. Correct. ID of 1 is equal to 1. Also, oh, I have to use some other notation. This is very bad notation. So I forgot what name we use for 2, 3. It is S, correct. S of 1 is equal to 1 as well. So the stabilizer of ID comma S, whereas orbit of 1 is 1, 2, 3. Okay, in that example. So observe that by definition, it's pretty clear. This is a subgroup of X. Orbit is a subgroup of X. Stabilizer is a subgroup of G. Okay. What else can you observe? It's very small example and you cannot generalize like that from one example. But when you multiply the orders, or not order, multiply the size of the orbit or length of the orbit, it's not a group or anything, so just size or length of the orbit, multiplied by order of the stabilizer, because stabilizer is indeed a subgroup, you can easily prove it. This is equal to, okay, it's actually confusing because I took set also of size 6. So misleading, sorry, but it's actually order of S3. Okay, I have to prove it. It is order of S3, nothing to do with X. It is order of S3. Okay, unfortunately, I should have taken 7, 8, 9 also and defined it similarly. Obviously, I can take 7, 8, 9 and define like this. R of 7 is equal to 8 and so on. So in that case, the stabilizer actually remains the same. But the orbit also remains the same. Correct. Orbit and stabilizer will remain the same if I extend the set with 3 more elements and similarly write. So the order has to be this. I mean, this product has to be the order of S3, not size of X. Okay. Yeah, the first question is prove that orbit is equal to this. That's because in the notes I defined orbit in a different way. You can define orbit in this way. So if you take X, Y belonging to X, define an equivalence relation as follows. If X is mapped to Y by some G, by the action of some G, okay. This is Y. If there is some G such that G dot X equal to Y, then declare X to be equivalent to Y. This is an equivalence relation. Every element is equivalent to itself because 1 dot X is equal to X, so X is related to itself. That is true. Is it true that if X is related to Y, Y is related to X? Yeah, because then Y is equal to G inverse dot X. How do you know this? Huh? Oh, sorry, X equal to so why is that true? Just apply G inverse on both sides and use the second property. G inverse dot G dot X is G inverse G dot X. No, Got it. Anyone who didn't get this? G inverse dot G dot X is equal to, by second property of group action, it is equal to this, but this is equal to 1 dot X, which is by first property equal to X. Okay, so yeah, and this is Y, no? G inverse dot Y is equal to X. Okay, so that's true. And transitivity follows directly from second property again. Just second property, you get transitivity. So this is an equivalence relation. So the class of X under this equivalence relation, class of X under this equivalence relation is exactly the orbit of X. Okay. Many books define it that way. In the notes also I've defined it that way. You can define it the other way also and then show that this is true. Okay, whatever way you define, you show that it's equal to the other one. Okay, so pretty obvious that it's equal to this. Once you show that it's an equivalence relation, clearly that is equal to this, because by definition, any element is equivalent to X under this relation if and only if it can be written as G dot X. So that's exactly what we wrote as the definition of the set. It is a set of all G dot X, right, for that fixed X. Yeah, so that is orbit of X. But now observing that this is an equivalence relation tells you something. What? Because the orbits are equivalence classes, what do they do to X? They partition X. So when you take the group action X, this is orbit of some X1, orbit of X. Okay, we don't require any finiteness or anything, but okay, let's assume the finite case for proving the lemma anyway. So yeah, consider the finite case. So you actually have so many distinct orbits. Okay, this is partition. X is partitioned into this. How is all this related to the stabilizer? How do you relate this to the stabilizer? Okay, first question. What is stabilizer of G dot X? If X is in terms of stabilizer of X, can you write stabilizer of G dot X? Is it equal to G times stabilizer of X? Remember, stabilizer of X is a subgroup. You can prove that. So you can definitely multiply G with it and form a coset and so on. But is it equal to that? Stabilizer of Gx means what? You need an element H. You need an element H. I mean, H is in stabilizer of G dot X means H dot X is equal to X. I mean, H dot G dot X equal to X. That means X is mapped to its G dot X is mapped to itself under the action of H. You should really think of group elements as functions acting on the set, permutations acting on the set. Okay, so H should stabilize this. I need to somehow relate this to the stabilizer of X. How can I do that? You take X. Yes, you have something? G inverse X inverse, G inverse H inverse, yeah. Okay. So in fact, G inverse HG also. Right. Is that true? Yeah, of course, that has to be true. I would go in the other direction. But yeah, when you think about it, you may come upon it in this direction. So what you're doing is G inverse. G inverse will map this back to X. Correct. G inverse will map this. Oh, no. I see what you did. Yeah. So you are saying G inverse H inverse G. So when you write G inverse H inverse G, what are you applying first? If you're applying this to anything, you're saying that this dot X is equal to X is your claim. So what is being applied first? G, not G inverse. So first you take G and go here. Okay. Applying G will take you from X to G dot X. Should really think of it that way. Then you are applying H inverse. You might as well as apply H, because anyway everything stabilizes. Okay, I know. You want to prove that directly. Fine. So if you apply H inverse, what happens? We are assuming that H is there in the stabilizer, so H inverse will map it to itself. You will stay there, and then you are applying G inverse. Where does it take you? Back to X. So you're saying that G inverse H inverse X, sorry, G belongs to stabilizer of X. That means H inverse belongs to G stabilizer of X, G inverse, or equivalently, because the subgroup H belongs to same thing. This is also a subgroup. Okay, so if H inverse is there, H is also there. Okay, and conversely, converse is also true. Whatever you did here, you can reverse. So actually, I would have gone this way. I want to stabilize G dot X. I'm starting from G dot X. I know that if I apply G inverse, I can come to X. Then I apply some element in the stabilizer of X. So some, let's say some sigma. So I'll stay there, and then I'll use the inverse of this to go back. Okay, that means G to go back. So if I compose the three, I will get H. So just that way, right? So I can say that any element of the form G sigma G inverse, where sigma is from stabilizer of X, this will belong to stabilizer of G dot X. And conversely, if I take an element in stabilizer, I can do the same thing and get them. So they are equal. Okay. So in fact, this is equal to that proves that cardinality of stabilizer of X is equal to cardinality of stabilizer of Y for all Y, where in the orbit of X, because G dot X means some element of the orbit. So any two elements in the same orbit have stabilizers of the same order, not equal stabilizer, stabilizers of the same order. We're only doing counting now. This is true. So that does problems 9A, C, and D. P is just proving that subgroup. It's easy. So A, C, A, and D are done. Yeah. Okay. So next problem I'm not doing, but you can similarly prove that. Suppose you take, instead of asking for stabilizer, what elements of the group fix a particular point, you can also ask what elements of a group map a given point to another point. Okay. Which are the elements of the group that map a given point to another point. So you call this gxy or whatever. I'm just making up this notation. So let gxy be g in g such that g dot x equal to y. Okay. I mean, when is it defined? When is gxy in terms of x and y? When is gxy defined? When y is in the orbit of x. Otherwise, you don't. Otherwise, you get empty set. You can say. Right. So I'm only going to consider this where y is in the orbit. Okay. So you can also prove that gxy is okay. That's easy. Gxy is obviously equal to g times stabilizer of x for in fact for that's not a good way of saying let y equal to g dot x. Yeah. So then clearly gxy is equal to g times stab of x. So this again proves that cardinality of gxy, it's not a subgroup. It's in fact a coset of this, as you can see, is equal to cardinality of this, right? Now, if you take all the distinct gxy, okay, whatever that is, for all the distinct elements y1, y2, etc., yk in the orbit of x, is this a partition of G? Any element of G has to map x somewhere. Somewhere means where? Somewhere in the orbit. So if you take any element in the orbit, or rather if you take any element G, you will get some such element y, so that you get the gxy. So this will partition G. This is a set, and so on. This is a partition of G, correct? So order of G in the finite case, order of G is equal to order of gxy1, etc. Order of G xy k, where y1, y2, etc., yk are distinct elements of the orbit. All the distinct elements of the orbit. Is that correct? So the question is, can any two of them be the same? Obviously not, because whatever is here maps x to y1. If I take a different y2, those elements map x to y2, so they cannot be the same element, right? So this is true, but each of this is equal to what? So each of this is equal to order of the stabilizer. Order of the stabilizer. So this is k times or something times stabilizer. Something means that k. What is it k? Number of distinct elements in the orbit. Number of elements in the orbit. So that is orbit stabilizer lemma or orbit stabilizer theorem. Okay. Yeah. So that exercise basically proves it. If you do those problems one by one, you get this. Fine. So we'll stop for today. Or you want to continue? Okay.